Welcome to another deep dive. Today we're looking at a paper you sent us called Periodic Symplectic and Hamiltonian Diffeomorphisms on Irrational Ruled Surfaces. And, well, it sounds pretty complicated, but I think we can unpack it.
Yeah, it's a fascinating area of research. I think the paper starts off with a pretty fundamental question that has driven a lot of recent work.
Yep.
Can every Hamiltonian cyclic action be extended to a Hamiltonian circle action?
So right off the bat, they're hitting us with something that sounds deceptively simple. Like, is the answer just yes or no, or is there something more to it?
It's definitely more nuanced than a simple yes or no. The paper kind of breaks it down and explores this question through different types of symplectic four manifolds. So they look at rational surfaces, irrational ruled surfaces, and the non-uniruled surfaces.
Okay, so the type of space we're working in matters.
Yeah.
Let's start with, I guess, what might be the easiest, the rational four manifolds. What do we know about them?
For rational surfaces, particularly those that are related to complex projective spaces, it seems like the answer might be yes in a lot of cases. But there are already some known exceptions, particularly when you're dealing with things called involutions.
Involutions, so like reflections that when you do them twice, you get back to the starting point, right? So even in these, I guess what we might consider the well-behaved rational surfaces, there's already some surprises.
Exactly, yeah. There's some previous research cited in the paper where they found symplectic involutions on certain rational surfaces that just refuse to extend to circle actions.
It seems like even the simpler cases have their own little quirks and mysteries going on. But this paper focuses on irrational ruled surfaces. So what makes them so interesting to study?
I think irrational ruled surfaces kind of occupy this middle ground. They're more complex than rational surfaces, but they're not quite as wild as the non-uniruled ones. So they're kind of this fertile testing ground for this question of expending actions.
Before we go any further, I think it would be helpful to define what exactly an irrational ruled surface is, just so everyone's on the same page.
Sure. So basically, you can think of an irrational ruled surface as being constructed by taking a sphere like our familiar S2,
Yeah.
and then you fiber it over a surface that's not a sphere. So imagine something like a donut or a pretzel, where each point on that donut or pretzel has a sphere attached to it. That kind of gives you a visual of what we're dealing with.
Okay, so I'm picturing it. We have these irrational ruled surfaces and the spheres attached to them. What does the paper say about extending cyclic actions on those surfaces?
This is where it gets really interesting. So one of the main results in the paper is theorem 1.2. And what they do is they actually construct explicit examples of symplectic involutions on these surfaces that cannot be extended to circle actions, even if you allow the underlying symplectic form to change.
Wait, so there are specific ways to reflect an irrational ruled surface that just can't be smoothed out into a continuous spinning motion. That's very counterintuitive.
It is, yeah. And the way they prove this is actually pretty clever. They use fixed points as kind of a smoking gun. So any Hamiltonian circle action on a minimal irrational ruled surface has to fix two special sections completely.
Hold on, can you remind me what minimal means in this context when we're talking about an irrational ruled surface?
Right, good point. So a minimal irrational ruled surface is one that hasn't been blown up. Imagine you take your donut and you start adding extra handles to it. That's like blowing up a surface. A minimal surface is kind of the simplest version without any of that extra complexity added on.
Okay, so we have these minimal irrational ruled surfaces and the circle actions fixed two sections. What about other cyclic actions? Do they behave the same way?
So the paper shows that most cyclic actions, meaning those with order greater than 2, also have to fix those same two sections. But for these specific involutions they construct, there's only one section fixed, and that's their smoking gun. That's the key to proving that these actions can't come from circle actions.
So the fixed point set kind of gives away the nature of the symmetry. It can't come from a circle action if it doesn't fix two sections.
Exactly. Now you might be thinking, well, does that mean extending cyclic actions is always impossible on these surfaces? But that's not the case either. The paper actually proves that for cyclic actions of order greater than 2, you can always extend them to Hamiltonian circle actions.
So it's like a yes for orders greater than 2, but a hard no for involutions. That's a pretty stark difference.
Yeah, and it really highlights this fundamental distinction between involutions and other cyclic actions in symplectic geometry. They really behave in fundamentally different ways.
Okay, so this is already pretty mind-bending. I'm curious to know how they actually prove these results.
Yeah.
What kind of mathematical tools are we talking about here?
They go into the world of J-holomorphic curves, which are powerful tools in symplectic geometry. These curves are generalizations of surfaces that meet certain complex geometric conditions.
J-holomorphic curves. It sounds like that's a whole other deep dive in and of itself.
It definitely is. But for now, let's just focus on two key concepts that they use, which are moduli maps and evaluation maps.
Okay, so moduli maps and evaluation maps. What are those all about?
So think of the moduli map as a blueprint that tells us how all of the J-holomorphic spheres are arranged within the surface. And the evaluation map lets us track the movement of these curves as we move points around on the surface.
So by setting these maps, they can actually see how the symmetry is acting on the whole surface.
Exactly. It's like putting the irrational ruled surface under a microscope and watching all the intricate mechanisms at play. They can see how the fixed points, the J-holomorphic curves, and the symmetries themselves all relate to each other.
This is fascinating stuff. So we have the basic setup, we have the surprising twist with the involutions, and we have a glimpse into the tools they're using. What else does the paper explore?
Well, they don't stop there. They also tackle the classification of all possible finite groups of symplectomorphisms that can act on these irrational ruled surfaces.
Ooh, okay, tell me more.
And it turns out they're all related to subgroups of SO3, which is the group of rotations in 3 dimensions.
That's interesting. Even though we're in 4 dimensions, the possible symmetries are constrained by what happens in 3 dimensions.
Yeah, exactly. And they don't just classify the groups, they also really delve into the fixed point sets of these actions. And again, they show how involutions behave differently from other cyclic actions in this regard.
I'm ready for more. What about those exotic involutions you mentioned? How do they actually construct those?
That's where the real fun begins. They actually provide a step-by-step recipe. So they start with a double cover of the surface, and then they very carefully choose an invariant circle within that double cover. Then, using a special embedding and an invariant symplectic form, they create an involution that has a very specific property. Its fixed point set is connected, and that's the key that prevents it from being extended to a circle action.
It sounds like they're building these bizarre symmetries from scratch,
Yeah.
using some kind of mathematical origami.
I like that analogy. And it doesn't end there. They even go on to generalize these exotic involutions to higher dimensional spaces, like 6-dimensional manifolds.
Wait, we're going beyond 4 dimensions now.
We are. The basic ideas carry over, but the geometry gets even more intricate. They create even more exotic examples in these higher dimensions, which shows that non-extendable actions are surprisingly common.
This paper is like a mathematical rabbit hole leading to deeper and deeper levels of complexity.
It truly is. And it culminates in a discussion of how these findings impact that fundamental question we started with about extending cyclic actions. It gives us a much deeper understanding of the limits and the possibilities of symplectic symmetries.
I'm starting to realize that even in what might seem like well-understood areas of math like symplectic geometry, there are still these vast uncharted territories. And this paper gives us new tools and ideas to explore them.
Absolutely. And it opens up all sorts of new questions. What happens in even higher dimensions? Are there other types of exotic actions waiting to be discovered? This paper is kind of like a launching pad for a whole new generation of mathematicians to grapple with these questions.
This has been an amazing journey so far. But I think we need to pause here and let all of this sink in. We'll pick up the rest of this discussion in part 2 of our deep dive.
Welcome back. So we left off talking about how the authors actually build these exotic involutions that can't be extended to circle actions, and it's pretty ingenious how they do it.
Yeah, I'm really curious to hear the specifics of how they construct these symmetries from the ground up.
Yeah.
Where do they even begin?
They start with this clever observation that every compact orientable surface of genus, at least one, has what's called a double cover. So you can think of it as taking 2 copies of your surface and gluing them together in a very particular way. And this double cover comes with a natural involution, which is just a way to swap the 2 copies.
Okay, I'm trying to visualize that. So we have this double cover, and it has this built-in reflection symmetry. What do they do with that?
Well, the next step is to find a circle embedded within this double cover that's invariant under that involution. So imagine finding a line of symmetry on the double cover that also happens to be a circle.
That sounds pretty tricky. Is it always possible to find such a circle?
Yes, it is. And the authors actually show how to do this using something called an equivariant retraction. It's a way to map the entire double cover onto the circle, but in a way that respects the involution.
So they're collapsing the double cover onto this special circle, but in a way that preserves the symmetry I'm following so far. What happens next?
Here's where it gets really clever. They take this invariant circle and they embed it into a new space, which is the product space, SX, S2, where S is our original surface.
I'm trying to understand the logic here. Why move to this product space? What happened to the double cover?
The double cover is still there, kind of lurking in the background. But by embedding the invariant circle into SXS2, they're essentially transferring the symmetry from the double cover into this new space.
So they're setting up a way to create a symmetry on SXS2 that reflects the symmetry from the double cover.
Precisely.
Yeah.
And here's the brilliant part. They construct a specific involution on SXS2 whose fixed point set is exactly this embedded double cover.
Hold on. The fixed points of this new involution form an entire surface, not just a collection of points.
You got it. That's what makes this construction so remarkable. They create an involution where the fixed point set is a connected bisection of SXS2.
By bisection, you mean it intersects each sphere fiber in 2 points, right?
Exactly. And that's the crucial property that guarantees this involution can't be extended to a circle action. Remember, a circle action would have to fix 2 distinct sections, not a connected bisection.
Ah, I see. The shape of the fixed point set gives it away. It can't possibly come from a circle action.
Now, of course, to make all of this work, they need to equip SXS2 with a symplectic form that's compatible with this exotic involution. And they do this by combining the standard product form with a form that they pull back from the original surface.
So they're carefully tailoring the geometry of this product space to accommodate this unusual symmetry.
Exactly. And they show that by choosing the right combination of forms, they can create a symplectic structure that fits this exotic involution perfectly.
This is incredibly intricate. It's amazing how they can build these symmetries step by step.
You mentioned earlier that they generalize these exotic involutions to higher dimensions. How do they manage to do that?
The key to extending the construction is finding a way to transfer that involution from a double cover to a more general product space.
So they need some kind of higher dimensional analog of that invariant circle embedding we talked about.
Exactly. And to do this, they bring in the concept of a finitely presented group. It's a way to capture the fundamental structure of the space and its symmetries, using tools from algebraic topology. I'm sensing a pattern here. They use algebraic tools to understand the topology, and then that guides their construction of the symplectic geometry.
You're exactly right. It's this beautiful interplay between different areas of math. And in this case, they show that if you have a space whose fundamental group satisfies certain conditions, then you can always find a way to transfer an involution from a double cover to a product space.
So they've created a kind of recipe for generating these exotic involutions in higher dimensions.
Precisely. And to show off this recipe, they construct explicit examples in 6-dimensional manifolds, which proves that these non-extendable actions aren't just some weird quirk of 4 dimensions. They're a fundamental aspect of symplectic geometry in general.
It's incredible how this paper is opening our eyes to just how vast and complex these mathematical structures really are.
It really is. And they don't stop there. They go on to consider actions of what's called the Klein-4 group, which is a group with 4 elements.
Remind me what's special about the Klein-4 group.
It's the simplest non-cyclic group, which means it's not generated by a single element. It has 3 involutions and the identity element. And the authors show that you can construct exotic actions of this group on irrational ruled 4 manifolds as well.
So they're building symmetries with multiple layers of exotic behavior. How do they pull that off?
They use this really clever trick based on the symmetry of 3 different embeddings of a circle relative to a pair of antipodal points on a sphere. It's kind of hard to visualize without diagrams, but they essentially create 3 separate embeddings of the double cover into SXS2, each linked to one of the involutions in the Klein-4 group.
So they're constructing an action where none of the 3 involutions can be extended to a circle action.
Exactly. And they even show that this entire Klein-4 group action can't be extended to a larger symmetry group called SO3, which is the group of all rotations in 3 dimensions.
It's like they're creating symmetries that are fundamentally incompatible with those familiar rotations.
Exactly. And that highlights a really crucial point. These exotic actions aren't just some mathematical curiosities. They reveal these deep connections between different areas of math, like symplectic geometry, algebraic topology, and group theory. And they challenge our assumptions about what kinds of symmetries are even possible.
This has been an incredible journey so far. I feel like we've only just scratched the surface of this paper.
You're absolutely right. We still need to talk about how the authors actually use J-holomorphic curves to analyze these symmetries and prove their remarkable results.
That sounds like the perfect topic to delve into in the final part of our deep dive. Welcome back to our deep dive. We've spent the last 2 parts really digging into those surprising findings about exotic involutions and their higher dimensional cousins. But we haven't talked much about how they actually use J-holomorphic curves to get there.
Right. J-holomorphic curves are these incredibly powerful tools in symplectic geometry. They give us a way to see the structure of these symplectic manifolds in a way that kind of goes beyond traditional methods. In this paper, they play a huge role in understanding how these cyclic actions we've been talking about operate on the irrational ruled surfaces.
You keep saying J-holomorphic curves. Can we just back up for a second and remind ourselves what those are exactly? It sounds a little intimidating.
Yeah, it's kind of a mouthful, I guess, but they're really not as scary as they sound. Imagine a surface like a sphere or a donut embedded in your symplectic manifold. A J-holomorphic curve is a special kind of surface that satisfies a certain geometric condition. And that condition comes from something called an almost complex structure, which is usually denoted by J-pers. Think of it as a surface that's like perfectly aligned with the geometry that's determined by the symplectic structure.
So it's like a surface that's in harmony with the symplectic form. Okay, I'm getting a little bit of a picture, but how do these curves actually help us understand symmetries?
So the key is that symplectomorphisms, which are the maps that preserve the symplectic structure, they also interact beautifully with these J-holomorphic curves. The authors use this interaction to analyze how cyclic actions, which are generated by repeatedly applying a symplectomorphism, behave on the irrational ruled surface.
So the J-holomorphic curves act as probes to sort of reveal the workings of these symmetries. But how do they use these probes? What's their approach?
They combine two really important concepts called moduli maps and evaluation maps. So the moduli map is essentially like a map of all the J-holomorphic curves inside our surface. Think of it like a blueprint of the internal structure.
Okay, so the moduli map tells us how the curves are arranged, like a roadmap of the surface. And what about the evaluation map? How does that fit in?
The evaluation map basically lets us track the movement of these J-holomorphic curves as we move points around on the surface. So it tells us how the curves change as we apply a symplectomorphism.
Okay, we have a map of the curves, and we have a way to track their movement. So how does that all come together to help us understand these symmetries we keep talking about?
The authors use these maps to gain insights into the fixed point sets of these cyclic actions. And they show that for cyclic actions of order greater than 2, the fixed point set always consists of 2 disjoint sections.
Right, we talked about sections before. They're those special curves that intersect each sphere fiber in just one point.
Right, exactly. The fact that cyclic actions of order greater than 2 always fix 2 disjoint sections is super important because it helps them prove that these actions can always be extended to those Hamiltonian circle actions.
Okay, so the fixed point set really tells us whether or not we can extend the action. But how do they actually construct this extension? How do they go from something discrete to something continuous?
It's a beautiful argument based on Möbius transformations. Remember that each fiber of an irrational ruled surface is a sphere. Möbius transformations are these special maps that preserve the complex structure of a sphere. So they're ways to like rotate and stretch a sphere, but keep its essential shape intact.
We're bringing in complex numbers and spheres now. This is getting pretty advanced.
I know, right? But it's so elegant. They show that you can actually extend a cyclic action on each fiber to a continuous circle action by carefully choosing a family of Möbius transformations. It's like smoothly interpolating between those discrete jumps of the cyclic action.
So they're using these Möbius transformations to fill in the gaps and create a continuous flow from the discrete action. That's amazing.
Exactly. And they don't just stop there. They actually show how to extend the circle action to the whole irrational ruled surface using the information from those moduli and evaluation maps. It's like they're stitching together all those little circle actions on each fiber to make one big global circle action.
Like a bunch of spinning spheres that are woven together to make a continuously rotating fabric.
Exactly. And the best part is that this global circle action also preserves the symplectic structure. So it's a Hamiltonian circle action. They achieve what they set out to do, extend the cyclic action to a full-fledged Hamiltonian circle action.
Wow, this has been a seriously mind-blowing deep dive. We started with a pretty simple question about extending symmetries, and we ended up diving into symplectic geometry and J-holomorphic curves and Möbius transformations. It's amazing how all these different areas of math come together.
It really shows you how interconnected math really is. This paper is like a perfect example of how powerful it can be to look at a problem from multiple perspectives. By pulling insights from all these different fields, the authors were able to make these really profound discoveries about the nature of symplectic symmetries.
It's a great reminder that math isn't just a bunch of random facts, but a beautiful web of interconnected ideas. And papers like this help us see those connections and push us to explore even deeper.
Absolutely. And even though we've covered a lot of ground in this deep dive, this paper is really just the beginning. It opens up tons of new questions and research directions for mathematicians to explore. Who knows what other amazing things are waiting to be discovered in the world of symplectic geometry?
That's the beauty of math. There's always more to learn. And thanks to papers like this one, we have the tools and inspiration to keep pushing the boundaries of knowledge. Thanks for joining us on this incredible exploration.
Welcome back for another deep dive.
Okay.
Today we're going to be talking about symplectic geometry, and in particular, irrational ruled surfaces. We're looking at a paper by Nicholas Lindsay and Weiyi Zhang
Okay.
called Periodic Symplectic and Hamiltonian Diffeomorphisms on Irrational Ruled Surfaces.
Oh,
Great.
yes.
Sounds exciting.
Yeah, this is a really cool paper. So this paper is about the question of extending symplectic cyclic actions to Hamiltonian circle actions. So, can you always sort of embed a periodically repeating symplectic diffeomorphism into a circle action?
Yeah. I guess to set the stage a little bit, this paper is specifically focusing on irrational ruled surfaces. Could you remind everybody what those are?
Sure, yeah. So a ruled surface is, it's a surface which is a union of lines, kind of like threads.
Right.
And so you can imagine like taking a curve and then like moving a thread along that curve, and that sweeps out a surface.
Yeah.
So that would be a ruled surface.
Right.
And irrational just means that the base curve is not a simple closed curve. So it's more complicated than just a circle.
Okay, cool. So
Yeah.
let's dive right in. Page 1, the abstract.
Okay. So the abstract kind of lays out the main question of the paper,
Yeah.
which is, can every symplectic cyclic action be smoothly embedded into a Hamiltonian cycle action on an irrational ruled symplectic four-manifold?
Okay, four manifolds, always fun. So what do they find?
Well, they find that the answer is not always yes. It depends on the kind of cyclic action that you're looking at. So some things can be smoothly embedded,
Okay.
but other things, in particular certain involutions, are what they call exotic,
Okay.
meaning that they can't be smoothly embedded into a circle action.
Gotcha. All right, so page 2.
So on page 2, they start to sort of lay out the fact that this question can have different answers depending on the type of four-manifold that you're looking at.
Okay.
So so they break it up into, rational four-manifolds versus irrational ruled
Right.
versus non-uniruled. So for rational four-manifolds, there are some positive answers.
Okay.
There are also some counterexamples.
Right.
For non-uniruled manifolds, there's a conjecture,
Okay.
which is that there are no Hamiltonian periodic diffeomorphisms at all.
Gotcha. Interesting. So, but this paper specifically focuses on the irrational ruled.
That's right. Yeah. So they're focusing on irrational ruled four manifolds in dimension 4.
Okay.
And they're going to be looking at the case where the base curve has genus at least 2.
Okay, so things are getting a little more complicated. So page 3.
Yeah. So on page 3, they sort of start to give a slightly different formulation of the question. So instead of just asking about arbitrary symplectic cyclic actions, they ask about homologically trivial ones extending to Hamiltonian circle actions.
So homologically trivial, just meaning it doesn't change the topology in any way.
That's right. Yeah. So it acts trivially on homology.
Gotcha. Okay. And what comes out of that?
Well, one of the things that comes out of this is that there are exotic symplectic involutions,
Okay.
even on minimal irrational ruled surfaces. So these involutions cannot be smoothly embedded into a circle action, even if you're allowed to perturb the symplectic form a little bit.
And a minimal irrational ruled surface, just meaning it's sort of the simplest version of that type of space.
Right. It has the smallest possible value of B2.
Okay. Cool. So page 4, what's going on page 4?
So on page 4, they start to delve into the sort of what's special about these exotic involutions.
Okay.
What distinguishes them from other sorts of symmetries that you might have.
Okay.
And the answer lies in the fixed points of the involution.
Gotcha.
So previous work by Chang and Kessler relies on certain sort of four-dimensional geometric tools. But what Lindsay and Zhang do is they analyze the fixed point set. And the key point is that these exotic involutions have a connected fixed point set. Whereas, so for instance, if you were looking at like a Z3 action, the fixed point set would be disconnected.
Okay.
And that's why you can't extend it to a circle action.
Gotcha. So it's the fact that the fixed points are all connected that makes them special.
That's right.
All right. So on to page 5.
So on page 5, they sort of connect this back to some questions in complex algebraic geometry.
Okay.
So they point out that their construction provides an answer to a question of Weiyi Chen,
Mm-hmm.
who asked whether every symplectic automorphism of a complex surface can be viewed as coming from a complex automorphism
Okay.
of a surface, like a complex curve times a sphere.
Right.
And so so what Lindsay and Zhang show is that the answer is no. That these exotic involutions cannot be realized as complex automorphisms because their fixed point set is different from any fixed point set coming from a complex automorphism on a surface like a complex curve times a sphere. And moreover, they can't be extended to circle actions, even if you allow yourself to deform the symplectic form a little bit.
Oh, interesting.
Okay.
Okay, so page 6.
Okay, so page 6, they kind of switch gears a little bit.
Okay.
And they start talking about more general group actions.
Mm-hmm.
So they say that for the rest of the paper, they're going to be, sort of step by step, proving stronger and stronger results about the structure of fixed point sets and invariant curves, leading up to the main theorems about extending actions. So in particular, they're going to classify finite groups of symplectomorphisms acting trivially on homology. And they're going to be able to extend these exotic involutions to exotic actions of the Klein 4 group.
Interesting. Okay, cool. So pages 6 through 13 kind of lay the groundwork for all that.
That's right.
So what are some of the things that they talk about in those pages?
So one of the things they start with is a result from the Nielsen-Thurston classification of surface transformations, which says that if you have a periodic diffeomorphism of a surface of genus at least 2, which acts trivially on homology, then it has to be the identity.
Gotcha. So it can't actually move anything around.
That's right.
Okay. Interesting. What else?
Let's see. They talk about almost complex structures,
Okay.
which are, a way of sort of putting a complex structure on a manifold, even if it doesn't necessarily have a complex structure naturally.
Okay.
And they use this to define the moduli map.
Okay.
Which is, a map that sort of describes the irrational ruled surface as a bundle of spheres.
Okay.
They define weights for cyclic group actions, which is essentially how the action rotates the tangent space at the fixed points.
Gotcha.
They talk a little bit about Maruyama's classification of automorphism groups of ruled surfaces. So that has to do with, what are the possible groups of symmetries that can act on a ruled surface?
Okay.
And in particular, a surface, a product of a complex curve and a sphere has a more restricted group of symmetries than a general ruled surface.
Interesting.
And then finally, they sort of give a little bit of background on the main question of the paper, which is, whether or not you can extend symplectic cyclic actions to Hamiltonian circle actions. And they point out that, this depends on whether the manifold is uniruled or not.
Okay.
So uniruled manifold is one that can be covered by rational curves.
Gotcha.
Okay.
All right. So then page 14 is where they really start to get into the meat of the paper.
Yeah, that's right. So this is where they're really going to start using the techniques of pseudo-holomorphic curves to study finite symplectic actions on irrational ruled 4 manifolds.
Okay.
So proposition 3.1 says that if you have a finite group acting effectively on your manifold, and it's acting trivially on homology, then you can find a compatible, almost complex structure and a fibration over a sphere such that the group action preserves each fiber.
Okay. And effectively just meaning that it's actually, it's not trivial on each of the fibers.
That's right. So every element of the group, other than the identity, acts non-trivially on each fiber.
Gotcha. Okay. So then page 15.
So on page 15, they sort of move from the existence of these nice vibrations to classifying the possible groups that can act on an irrational ruled surface.
Okay.
So corollary 3.3 says that any finite group of symplectomorphisms acting trivially on homology has to be isomorphic to a finite subgroup of SO3.
Gotcha. So SO3 being the group of rotations of the sphere.
That's right, yeah.
Okay. So that limits the options quite a bit.
That's right, yeah. So it could be a cyclic group, it could be a dihedral group, it could be the symmetry group of a Platonic solid.
Okay, cool. So then 15 through 18, they start going into more detail about the different types of symmetries.
That's right. So they start looking at fixed point sets.
Okay.
So they begin by considering cyclic actions of order k bigger than 2.
Okay.
So these are rotations by a fraction of a turn where the fraction is not 1/2.
Right.
And proposition 3.5 says that in this case, the fixed point set has to consist of 2 disjoint sections of the fibration.
So 2 different curves that are each intersecting the sphere once.
That's right.
Okay.
And then they consider involutions.
Okay.
So this is when k is equal to 2.
Right.
And proposition 3.7 says that the fixed point set could either be a bisection, which is a single curve that intersects each fiber twice,
Okay.
or 2 sections.
Okay.
So similar to the case for k bigger than 2.
Gotcha. So the key takeaway from this is that for involutions, the fixed point set could be connected,
That's right.
whereas for the other ones, it has to be disconnected.
Exactly.
Okay. Cool. So 18 is where they start talking about the construction of the exotic involutions.
That's right, yeah. So now they're going to show that these involutions with connected fixed point sets actually do exist.
Okay.
And they can't be extended to circle actions.
Okay.
So they're going to do this in a few steps.
All right.
So first, they take a surface S of genus at least 1,
Okay.
and they consider its double cover S tilde.
Okay.
So this is a 2-to-1 covering space of S,
Mm-hmm.
and they find a circle in S tilde, which is preserved by the involution that exchanges the 2 sheets of the double cover.
Gotcha.
Okay. And then they use the circle to embed S tilde into S cross S2
Okay.
in such a way that it intersects each sphere fiber in a pair of antipodal points.
Okay.
So they've kind of arranged this double cover very carefully inside this product space.
Yeah.
And then finally, they define an involution on S cross S2
Okay.
by rotating each sphere fiber by 180 degrees around those 2 antipodal points
Okay.
where the double cover intersects it.
Gotcha. And they have to choose the symplectic form very carefully, right?
That's right. They have to choose a symplectic form so that this involution is actually symplectic.
Okay. Cool. And then that gives an exotic involution.
Exactly. So this is an involution that cannot be smoothly embedded into a circle action.
Okay. And then corollary 4.2 just says that these exist for any genus greater than or equal to 2 and any B2 greater than or equal to 2.
Exactly.
Okay, cool. So then 22.
So on page 22, they point out that this construction also answers a related question.
Okay.
So not only does it answer this question about extending involutions to circle actions, but it also shows that not every symplectic automorphism of a product of a complex curve and a sphere can be viewed as coming from a complex automorphism.
Gotcha.
So it gives you a sort of different way of seeing why these exotic involutions are special.
Gotcha. Okay, so then 23 is where they start talking about the Klein-4 group.
That's right, yeah. So now they're going to show how to extend these exotic involutions to exotic actions of the Klein-4 group.
Okay.
Which is a group that has 4 elements.
Right.
The identity and 3 involutions.
Okay.
So the idea is to kind of embed 3 copies of the double cover into S cross S2.
Right, so each of those is intersecting the sphere at 2 points.
Exactly. So each copy intersects the sphere fibers in a distinct pair of antipodal points.
Okay.
And then they define the 3 involutions of the Klein-4 group action by rotating each sphere fiber by 180 degrees around the corresponding pair of points.
Gotcha, okay. And that gives you...
And that gives you an exotic action of the Klein-4 group.
Okay, cool. So page 25.
All right. So on page 25, they sort of bring back this connection to algebraic geometry.
Right.
And they explain how these exotic involutions can be understood in terms of Maruyama's classification of automorphism groups of ruled surfaces.
Okay, so they're relating the geometry back to the algebra again.
That's right, yeah. They're showing how these 2 different perspectives can be used to understand the same phenomenon.
Cool, okay. So then page 26, they kind of switch gears again.
Right. So now they move back to considering cyclic actions of order Shea bigger than 2.
Okay, so no longer involutions.
Exactly. So these are the rotations that we were talking about before.
Right.
And they build up to theorem 5.1, which says that homologically trivial ZK actions for K bigger than 2 can always be extended to Hamiltonian circle actions, possibly after perturbing the symplectic form.
So this is in contrast to the involutions.
That's right.
Where sometimes you couldn't.
Exactly. So the involutions were special in that they could sometimes be exotic.
Gotcha.
But these ZK actions for K bigger than 2 can always be extended.
And why is that? Why are those different?
Well, it comes down to the fact that for A bigger than 2, the fixed points on each sphere fiber
Yeah.
come with a natural ordering.
Right.
And this allows you to uniquely define a circle action that extends the given ZK action.
Okay, so it's that ordering that makes it possible.
That's right.
Okay.
Okay.
So then theorem 5.2 on page 29, that's where they classify the actions.
That's right. So this is kind of a culmination of
Yeah.
all of their work.
Okay.
They classify all finite order symplectomorphisms acting trivially on the homology of an irrational ruled surface.
Okay.
And they show that any such action can be obtained
Okay.
by starting with a circle action on a minimal ruled surface
Okay.
and then performing some equivariant blowups.
Okay. So equivariant blowups meaning like you're adding in extra dimensions essentially.
That's right. You're replacing points
Okay.
with copies of CP1.
Gotcha. Okay.
But you're doing it in a way that preserves the symmetry.
Okay. Cool. And then the last theorem.
Right. So the last theorem, theorem 5.3, is on page 30.
Okay.
And this answers the main question
Okay.
for irrational ruled 4 manifolds, which are products of a surface and a sphere.
Okay.
So it says that if you have a Hamiltonian
Okay.
action for k bigger than 2,
Yeah.
then it extends to a Hamiltonian circle action.
Okay. So as long as it's Hamiltonian,
That's right.
and Hamiltonian just meaning comes from like a smooth energy function.
That's right.
Okay, cool. Well, this has been a really fascinating deep dive.
Yeah, it's a really nice paper.
It is a really nice paper. They cover a lot of ground.
They do, yeah. It's very impressive.
Yeah. What are your final thoughts?
Yeah, it's a great paper. It really shows you some of the surprising things that can happen in symplectic geometry.
Yeah, and it makes you think about like what are the bigger implications of all this? Like we've been talking about these exotic involutions and these ruled surfaces and these kind of weird restrictions on extending symmetries.
Yay.
But like, what does it all mean?
Well, I mean, I think one of the things it means is that, symplectic geometry is a very rich subject, and there's still a lot that we don't understand about it.
Yeah.
These exotic involutions are a really good example of that. Like, there's something that, we wouldn't have expected to exist based on our intuition from other areas of geometry.
Yeah, it's kind of breaking the rules a little bit.
Yeah, exactly.
But, I mean, I guess it also makes you think about, like, the applications, right?
Yeah.
So, symplectic geometry is used to model all sorts of physical systems. So, does this tell us something about the way that the world works?
Yeah. I mean, it's possible.
Yeah.
So, for example, if you have a physical system that exhibits some kind of periodic behavior, and that behavior is governed by an exotic symplectic involution, then that means that you might not be able to, smoothly embed that behavior into a continuous process.
Right. So it's kind of like fundamentally jerky in a way.
Yeah, exactly.
Interesting.
Yeah.
Well, this has been a great deep dive. I feel like I've learned a lot.
Yeah, me too.
Thanks for joining us, everybody. We'll see you next time. Welcome to the deep dive. We're diving into some pretty advanced math today.
Oh, yeah, definitely.
Yeah. Specifically, we're looking at this paper called Periodic Symplectic and Hamiltonian Diffeomorphisms on Irrational Ruled Surfaces. It's a mouthful.
It is. It is. But it's a fascinating paper. It really gets into the weeds of whether you can sort of smooth out certain kinds of transformations. We call them cyclic actions. Can we smooth them out into what we call circle actions? So imagine a clock, right? And the second hand is ticking. Tick, tick, tick.
Okay.
Can you make that ticking motion completely smooth? No more ticks, just constant motion.
I see, I see. So that's the kind of thing we're dealing with here. Transformations and whether they can be made, well, continuous.
Exactly. And the paper looks at this in the world of symplectic geometry, which I guess we should probably explain a bit.
Yeah, good point. So symplectic geometry, what is it really?
Well, think of it as a way of looking at shapes in spaces, but with a focus on a special kind of structure. We call it a symplectic form. And transformations that preserve this form, we call those symplectic diffeomorphisms.
Symplectic diffeomorphisms.
Ow, it's a mouthful, I know. But they're kind of like choreographed dances. Imagine dancers on a stage moving in specific ways. The distances and relationships between them stay the same even as they move. That's what these diffeomorphisms do. They preserve those relationships, those connections in the geometric space.
Okay, that's a helpful visual.
Yeah.
So they're all about keeping things in harmony, even while transforming the space.
Mm-hmm.
But then we have these special ones, right? The Hamiltonian diffeomorphisms.
Oh, yes. Those are generated by functions called Hamiltonians, which are really important in physics, especially classical mechanics. It's like adding a specific energy or rhythm to that dance we were picturing. It makes those geometric relationships dynamic.
Okay, so we've got our dances, those symplectic diffeomorphisms, and some have this extra rhythm, the Hamiltonian ones. But where are they dancing? What's the stage?
The stage in this case is something called an irrational ruled surface.
And that is?
Well, imagine a donut.
Okay, I can do that.
Now, imagine attaching a sphere to every single point on the surface of that donut. That's a basic picture of a ruled surface. The irrational part, that gets into some more technical details about the topology, but essentially, it influences how those transformations behave on the surface.
Got it. So we've got our dancers, our rhythm, and our stage. Now back to the big question. Can we always smooth out those ticks in the transformations? Can we always go from a cyclic action to a circle action?
That's the million-dollar question. And to answer it, the paper uses some pretty heavy-duty math tools, things like J-holomorphic curves, which are amazing for studying these symplectic structures.
Okay, I'm sensing this is going to get pretty complex.
It is. But
Yeah.
stick with us. It's worth it.
All right, lead the way. So, how does the paper start tackling this problem?
It starts by, laying the groundwork, defining all the terms, making sure everyone's on the same page. They talk a lot about how surfaces are classified and how we categorize the different ways they can be transformed. And they emphasize this thing called the base genus of the surface.
Okay, the genus of a donut, right? How many holes it has.
Exactly. And for these irrational ruled surfaces, the base genus really matters. It determines how those transformations will behave.
So it's like the genetic code of the surface influencing the entire dance routine.
That's a great way to put it.
So groundwork is laid. What's next?
Well, they bring up this really cool tool, the Nielsen-Thurston classification.
Okay. Refresh my memory on that one.
It's a way of classifying how surfaces can be continuously deformed. Like, how can you stretch or bend them without tearing or gluing anything?
Right, like Play-Doh.
Exactly. And the authors use this classification to prove something really important. Certain periodic transformations, the ones that eventually bring the surface back to its original state, have to actually be what we call the identity map.
Meaning?
They don't actually change anything. It's like going through a whole dance routine, lots of steps and turns, but ending up exactly where you started.
Oh, I see. So they look like they're doing something, but in the end, they're just a fancy way of staying still.
Exactly. And this is a key result because it helps simplify things. It lets them focus on the more interesting transformations, the ones that actually have a lasting effect on the surface.
Clever. So they've cleared out the decoys, so to speak. What do they do next?
Well, next, they bring in this concept of almost complex structures. It sounds a bit weird, I know.
Almost complex. It does sound a bit mysterious.
But it's actually a very powerful idea. It's like giving our surfaces a new set of tools based on complex numbers, those numbers with a real and an imaginary part.
Right.
Well, by equipping our surfaces with this almost complex structure, we can use all the tools from complex analysis to study them.
Like giving our dancers special shoes that let them do even more intricate moves.
Exactly. And then the paper introduces something called the moduli map. This helps us visualize these complex surfaces as fibrations. Think of it as a way of seeing the structure within those spheres we attached to the donut earlier. It's like those spheres are actually threads woven together to create a tapestry.
Ooh, I like that. So instead of just a jumble of spheres, we see this intricate woven pattern.
Precisely. And then the paper dives into something called the weights of cyclic group actions. These are numbers that tell us how strong the transformation is at a specific point on the surface and what direction it's pulling in. It's like understanding how each individual thread in that tapestry is being tugged or twisted.
So we're zooming in from the overall choreography to the movement of each individual dancer. What comes next?
Next, we get to the world of automorphism groups. These are groups that capture the symmetries of our irrational ruled surfaces.
Symmetries, huh? So like if you flip the tapestry over or rotate it, but it still looks the same.
Exactly. The automorphism group tells you all the different ways you can transform the surface while still preserving its fundamental structure. And the paper discusses Maruyama's classification of these groups. It's like a catalog of all the different symmetry patterns that are possible.
So depending on the shape of our stage, we have different dances we can do.
Precisely. And The paper highlights that simple ruled surfaces, those that are more like a plane cylinder, have a more limited set of symmetries compared to the more intricate woven ones.
The more complex the stage, the more intricate the dance moves can be.
Exactly. Now, are you ready to tackle the heart of the matter?
Bring it on.
All right. So we need to connect those finite order Hamiltonian diffeomorphisms, remember those?
The rhythmic dancers.
Yes. We need to connect them to the possibility of extending them to continuous circle actions. This is where our smooth upgrade question comes in.
Can we take those ticking clock hands and make them move smoothly and continuously?
Precisely. And the paper establishes a key result for surfaces. Any periodic Hamiltonian diffeomorphism, under the right conditions, can indeed be extended to a Hamiltonian circle action. It's like saying that any clock hand ticking in regular intervals has the potential to be transformed into a hand that sweeps smoothly around the clock face.
Okay, so on a surface, the answer is yes. We can make those smooth upgrades, but things get trickier in higher dimensions, right?
Right. We enter a whole new level of complexity when we move beyond surfaces. We need to consider different families of symplectic four manifolds, like rational, irrational ruled, and non-uniruled.
So our stage gets a whole lot more complex, and the rules of the dance might change depending on which type of stage we're on.
You got it. And that's where we'll pick up next time, diving into those higher dimensional complexity.
I can't wait. This is mind-blowing stuff.
It is, isn't it? The world of symplectic geometry is full of surprises.
Well, I'm eager to discover more. Until next time.
See you then.
Welcome back. So last time, we were starting to get into the really tricky stuff. Higher dimensions, different families of manifolds, and the question of whether we can still do those smooth upgrades from cyclic actions to circle actions.
Yeah, exactly. And as we hinted at, things get a lot more complicated in higher dimensions. Remember those exotic involutions we talked about? Those transformations that flip the space, but with a special kind of fixed point set?
Yeah, the ones that kind of break the rules.
Exactly. Well, they really throw a wrench in the works when it comes to those smooth upgrades.
So those exotic involutions, they can't be extended to circle actions.
Nope. The paper proves that pretty definitively. They actually use those exotic involutions as a counterexample to the idea that every Hamiltonian cyclic action can be extended to a circle action.
So just having a slightly different fixed point set completely changes the game.
It does. It shows how sensitive these transformations are to the structure of the space they're acting on. And it highlights that the relationship between discrete and continuous symmetries is way more subtle than we might think.
So it's not just a simple matter of smoothing out the ticks. Sometimes those ticks are fundamental to the transformation itself.
Exactly. And to drive this point home even further, the authors show that you can actually construct these exotic involutions in even higher dimensions.
Wow, so they're not just a weird quirk of four-dimensional space. They're like a fundamental feature of symplectic geometry.
It seems that way, and the surprises don't stop there. The paper also looks at these things called Klein four-group actions, which are another type of transformation, and they show that these can also be constructed in a way that prevents them from being smoothly extended.
Okay, so we've got these two different kinds of transformations, exotic involutions and these Klein four-group things, and they both resist being smoothed out. What's the takeaway from that?
Well, it shows that the relationship between discrete and continuous symmetries isn't always straightforward. We might think of continuous actions as just smoother versions of discrete ones, but that's not always the case. Sometimes the ticks are essential.
So it challenges our intuition about how these things work. We need to be careful about making assumptions.
Definitely. Now, to dig a little deeper into these exotic actions, the paper takes a look at their algebro-geometric realizations.
Uh-oh, more jargon? Break that down for me.
It basically means they're looking at these transformations from an algebraic perspective. It's like, we've been talking about these transformations in terms of shapes and spaces, but now we're going to translate all of that into the language of equations.
Okay, so we're switching from geometry to algebra, but still looking at the same transformations.
Exactly. And this algebraic perspective gives us some really powerful tools for understanding why these exotic actions behave the way they do.
It's like having two different lenses to look at the same object. We get a more complete picture that way.
Exactly. Now, even though we found these transformations that can't be extended to circle actions, the paper doesn't say it's never possible.
Well, there's still hope for those smooth clock hands.
There is. The authors show that for a certain class of transformations, specifically those with order greater than 2 that act trivially on homology, you can often extend them to circle actions.
So it's not all or nothing. There are specific types of transformations that can make the jump to continuous actions.
Right. But there's a catch. Sometimes this upgrade is only possible if we modify the symplectic form itself.
So we might need to tweak the stage a bit to make those smooth moves possible.
Exactly. It's like fine-tuning the mechanics of the clock to get those hands moving just right.
So it's not always easy, but it can be done.
Yep. And to wrap things up, the paper gives us a nice classification of these finite order symplectomorphisms that act trivially on homology, which is super helpful for understanding their properties.
So we've encountered these exotic involutions that break the rules, we've explored their algebraic side, and we've learned about when we can and can't make those smooth upgrades to circle actions. It's been quite a journey.
It has. This paper really highlights the depth and complexity of symplectic geometry, and it shows that even in well-established areas, there are always new things to discover.
Absolutely. And now I think it's time to take a step back and reflect on the broader implications of all of this. What do these findings tell us about the bigger picture of symplectic geometry and dynamical systems?
That's a great question, and that's where we'll pick up after a quick break. Stay tuned. Welcome back. We were just talking about the broader implications of these findings, especially how those exotic involutions and the whole question of extending actions might affect how we think about dynamical systems in symplectic geometry.
Yeah, it's a really intriguing area for future research. This paper focused on the existence and properties of these transformations, but it definitely raises a lot of questions about, how these results play out in the context of systems evolving over time.
It's like we've opened this door and we see this whole new wing of the library full of unexplored books. Exactly. But before we wander off too far, let's just take a minute to recap what we learned from this particular paper. We started by defining all the key players: symplectic diffeomorphisms, Hamiltonian diffeomorphisms, irrational ruled surfaces.
Right, our dancers, the rhythm, and the stage.
Exactly. And then we dug into the big question, right? Can we always smooth out those cyclic actions into circle actions, those ticking clock hands into smooth movement?
And it turned out to be trickier than we might have thought at first.
Definitely not a simple yes or no answer. The paper used some pretty fancy math tools, like that Nielsen-Thurston classification and those J-holomorphic curves, to show that sometimes you can make that smooth upgrade, but sometimes you can't.
And those exotic involutions were the real eye-openers, right?
Yeah.
They showed us that sometimes those ticks are actually essential to the transformation.
Absolutely. They really challenged our intuition about the relationship between discrete and continuous symmetries. And then there were those Klein four-group actions, too, which also resisted being smoothed out.
So we had these two different kinds of transformations, both kind of stubborn in their own way.
Exactly. And then when we delved into the algebraic side of things with those algebro-geometric realizations, we got to see why those exotic involutions behave the way they do from a whole new perspective.
It was like having two different sets of blueprints for the same machine.
Yeah.
It gave us a much deeper understanding.
All right. And then, even though we found those transformations that couldn't be extended, the paper showed that sometimes it is possible, especially for those transformations with order greater than 2 that are homologically trivial.
But sometimes we have to tweak the symplectic form a little bit, right?
Yeah.
Like adjusting the stage to make those smooth moves possible.
Exactly. It's not always easy, but it can be done. And the paper even gave us a helpful classification of those finite order symplectomorphisms.
It's been a really fascinating deep dive. We've uncovered some surprising results, challenged our assumptions, and gotten a glimpse into the incredible complexity of symplectic geometry.
Absolutely. It's a reminder that even in a field as well established as this, there are always new things to learn, new mysteries to explore.
A huge thank you to our expert for guiding us through all of this. It's been a pleasure.
The pleasure was all mine. Always happy to talk about math with such an engaged audience.
And to our listeners, if you're feeling adventurous, we encourage you to dive into the source material yourselves. There's a whole universe of mathematical wonders out there waiting to be discovered. Until next time, keep exploring. All right, let's dive into some pretty fascinating higher dimensional geometry today.
Sounds good.
We're looking at this paper, Periodic Symplectic and Hamiltonian Diffeomorphisms on Irrational Ruled Surfaces.
Okay.
It tackles a pretty intriguing question.
Right.
Can every Hamiltonian cyclic action be extended to a Hamiltonian circle action?
Interesting question.
Basically, can we always kind of smooth out a repetitive motion into a continuous rotation?
Mhm.
in these complex spaces?
Yeah, it's a question with some surprising answers, actually.
I bet.
And it really depends on what type of space we're working in.
All right.
The paper explores rational manifolds,
Okay.
rational ruled manifolds,
Right.
and non-uniruled manifolds,
Gotcha.
each with its own little quirks when it comes to this extendability problem.
So let's jump into the abstract.
Sure.
It mentions homologically trivial actions,
Mm-hmm.
and these things called irrational ruled symplectic four manifolds.
Right.
I have a feeling we'll be unpacking those terms quite a bit.
Yeah, definitely.
What does homologically trivial even mean?
So homologically trivial basically means the action doesn't fundamentally change the structure of our space. Think of it like rotating a donut.
Okay.
It's moving around, but the donut shape stays the same.
All right, I can picture that.
Yeah.
What about irrational ruled symplectic four manifolds?
They sound intimidating,
They do a little bit.
but they're not as bad as they sound.
Okay.
So picture this. You have a donut shape,
Okay.
and over every single point on that donut, you attach a sphere.
Whoa.
That gives you a rough idea of an irrational ruled four manifold.
Okay.
The symplectic part just means there's a special geometric structure there
Gotcha.
that kind of dictates how areas are preserved as things move around.
So the introduction dives into the history of this whole extendability problem,
Right.
breaking it down by the type of four manifold.
Yeah.
And it says that for rational manifolds, things are usually pretty straightforward.
Mm-hmm.
The answer is often yes.
Uh-huh.
But then when we get to rational ruled surfaces, which are bundles of spheres over a sphere,
Right.
things get a bit more interesting.
Half an hour.
What happens there?
Well, the authors highlight a known counterexample in this case. It involves something called a homologically trivial symplectic involution.
Whoa, another big word.
Essentially, it's like a specific way to flip a six-dimensional shape.
Okay.
Like a kind of a sphere with some extra dimensions that just can't be smoothly extended to a Hamiltonian circle action.
So even in spaces that seem relatively simple,
Yeah.
there are actions that resist this kind of smoothing out process.
Right.
Huh.
Exactly.
That's pretty wild.
It is, and that's why the paper focuses on irrational ruled four manifolds.
Makes sense.
They provide fertile ground for exploring this question,
Okay.
and as we'll see, they're full of surprises.
I've got the first big theorem, Theorem 1.2, really throws us a curveball.
Oh, yeah.
It states that even on a minimal irrational ruled surface,
Okay.
the simplest kind of irrational ruled surface,
Great.
we can find actions that can't be extended.
That's a big one.
So even tweaking the underlying geometry
Yeah.
won't help us smooth things out.
Right.
That's wild.
It is. And their method is really ingenious.
What did they do?
They introduce a new obstruction based on fixed point sets. Like imagine you're rotating a globe.
Huh?
The north and south poles stay fixed, right?
Yeah.
Those are fixed points.
Okay.
In higher dimensions, fixed point sets can be much more complex,
I bet.
forming shapes rather than just points.
Yeah, so how do these fixed points help us understand extendability?
Well, the paper shows that for an action to be extendable on a minimal irrational ruled surface,
Okay.
its fixed point set must have two separate distinct shapes called sections.
Interesting.
But the involution they construct has a fixed point set that's just one connected shape.
What?
It's like finding a way to rotate a globe so only a single continuous line stays still.
Whoa.
Yeah.
So by analyzing these fixed point sets, they kind of expose this fundamental incompatibility
Yeah.
between this specific involution and any potential circle action.
Right. It's like trying to fit square pegs into round holes.
I see.
The geometry just doesn't allow it.
And this has some interesting implications beyond just extendability.
It does.
Theorem 1.2 also answers another open question.
Right.
In mathematics,
Uh-huh.
does there exist a symplectic finite group action on a Keeler surface which is not equivalent to a holomorphic action?
Big question.
Yeah, hold on. Let's unpack that a bit.
Sure.
What are Keeler surfaces
Okay.
and holomorphic actions?
So think of a Keeler surface as a special type of complex manifold,
Right.
a space with a structure that allows us to define differentiation in a complex way.
Hmm.
And a holomorphic action is a way to transform that space
Stop.
that respects this complex structure.
Okay.
Like a perfectly smooth and symmetrical movement in a very intricate environment.
So what does this paper tell us about the connection between those two ideas?
The answer to the question is a resounding yes.
Really?
There are indeed symplectic actions that can't be replicated by any holomorphic action.
Wow.
It's another example of how seemingly distinct areas of math can have these unexpected
Okay.
and profound connections.
So even in these highly structured symmetrical spaces,
Right?
there are actions actions that break the mold
Mhm.
and defy expectations.
It's like finding a perfectly formed snowflake that's subtly different from all the others.
Right. My brain is officially doing backflips.
I can imagine.
Let's take a look at Corollary 1.4,
Okay.
which provides a concrete example of this yes answer. What's going on there?
This corollary dives into a specific case.
Okay.
It shows us an involution on a particular Kähler surface, a product of the complex plane and a projective line
Gotcha.
that just can't be mimicked by any holomorphic action on that surface.
Interesting.
It elegantly demonstrates that the world of symplectic actions is, in some ways, richer
Okay.
and more diverse than the world of holomorphic actions.
So even in these really structured, symmetrical spaces, there are actions that just break the mold
Right.
and defy expectations.
Yeah,
It's pretty amazing.
it is.
And these discoveries in four manifolds lead us to the next question. What happens in higher dimensions?
Right. What happens when we go up even further?
Do these unexpected complexities persist?
That's the question, isn't it?
Yeah.
And the paper doesn't shy away from that at all.
Good.
It takes us on a journey to six-dimensional spaces,
Wow.
showing that these counterintuitive findings aren't limited to 4 dimensions.
That's pretty wild.
It is.
Corollary 1.5 illustrates this.
Right.
The authors construct a homologically trivial symplectic involution
Yeah.
in 6-dimensional space, a product of surfaces and spheres
All right.
that, again, can't be extended
To a Hamiltonian circle action.
to a Hamiltonian circle action.
It's like they've taken those strange non-extendable actions from 4 dimensions and shown us they can exist in even more mind-boggling landscapes.
Okay, so now we're dealing with shapes and movements that are practically impossible to visualize.
Right.
How do they even prove that this 6-dimensional involution is non-extendable?
They use some really sophisticated tools from symplectic geometry.
Like what?
A key concept here is the moment map,
Okay.
which helps us understand the interplay between symmetries and conserved quantities in these spaces.
So it's a way to map the movements of our shape onto like a sort of energy landscape.
You could think of it that way.
Okay.
Yeah, by analyzing the moment map and the topological properties of the fixed point sets, the authors demonstrate that this involution just can't be smoothly integrated into a Hamiltonian circle action.
So it's like trying to find this perfectly balanced way to spin a complex multi-dimensional object
Right.
and then realizing that the geometry itself makes it impossible.
Yeah, exactly.
All right, need to catch my breath for a second.
Take your time.
So far, we've seen that involutions can be real troublemakers when it comes to extendability.
Yeah, they can be.
But the paper also explores another type of action called a ZK action. What makes these different?
So ZK actions have a very specific kind of rotational symmetry.
Yeah.
Imagine rotating an object by a fixed fraction of a full circle, rather than just flipping it like an involution.
And what do the authors discover about these ZK actions?
Interesting question.
Do they exhibit the same kind of resistance to extension?
Well, that's where things get even more mind-boggling.
Oh, no.
Yeah. The paper dives into the nitty-gritty of why that is.
Okay.
It all comes down to fixed point sets.
Right.
Imagine you're spinning a globe.
Right.
The north and south poles, they stay put right.
Right.
Those are fixed points.
Gotcha.
Now, in higher dimensions, fixed point sets get much more complex.
I can imagine.
But the idea is the same.
So how do these fixed points relate to our big question about extending actions?
Well, the paper shows that if we want to extend a particular kind of action,
Okay.
a ZK action, it all hinges on whether the fixed points can be divided into 2 distinct sets, or if they're all connected. It's kind of like asking if we can split a donut into 2 separate pieces, or if it has to stay as one whole.
Interesting. And what did they find? Can we always split those donuts?
That's where things get even more mind-boggling. For actions with a certain kind of rotational symmetry,
Okay.
think of rotating something by a third of a full circle or a quarter. The answer is yes. We can always extend them.
Wow.
But sometimes to make it work, we have to tweak the underlying geometry of the space a bit.
So it's like adjusting the shape of our donut
Exactly.
to make sure it splits cleanly.
Right.
So it's not always a simple yes or no answer.
It's not.
It depends on the specific action.
Right.
Even the shape of the space that we're working in.
Exactly. And this paper does a fantastic job of mapping out all the different possibilities,
Okay.
showing us precisely when an action can be extended and when it can't. It's good.
And they even provide a complete classification of all the different types of transformations
okay.
that preserve a certain geometric structure. It's like creating a detailed catalog of all the ways we can rearrange a complex puzzle while still keeping its overall shape intact.
So by diving deep into these abstract mathematical concepts,
Yes.
the paper reveals this hidden order and structure
Right.
within this complex world of transformations.
Precisely. And that's the beauty of mathematics.
I agree.
It lets us see these patterns and connections
Yeah.
that would otherwise be invisible to us.
So what's the takeaway for someone who isn't a mathematician, but is fascinated by these ideas?
I think the biggest takeaway is that even in the most abstract realms of thought,
Okay.
there's always something new to discover.
You're right.
This paper shows us that even seemingly simple questions
Yeah.
can lead to profound insights into the nature of space,
Okay.
symmetry, and transformation. It makes you wonder what other mathematical mysteries are out there,
Absolutely.
just waiting to be uncovered.
And who knows, maybe one day some of these abstract concepts will find applications
I could see that.
in fields like physics or engineering or computer science,
Yeah.
helping us to better understand
Okay.
and manipulate the world around us.
Well, this deep dive has definitely left me with a lot to think about.
Me too.
I think I need to go lie down and contemplate the nature of higher dimensional spaces for a while.
I understand completely.
It's been a pleasure exploring this fascinating paper with you.
Likewise.
And to our listeners, I encourage you to delve deeper into these concepts.
Absolutely.
Who knows what mathematical mysteries you might uncover?
Yeah, and if you find yourself getting lost in a six-dimensional labyrinth,
I can imagine that happening.
don't worry. That's perfectly normal.
Right.
Even the experts get disoriented sometimes.
Yeah, I bet.
The key is to embrace the challenge
Okay.
and enjoy the journey of discovery. Until next time, happy exploring.
Yeah, and this paper goes even further.
Oh, really?
It dives into even more specific cases.
Okay.
And gives us a complete classification of finite order symplectomorphisms.
Those are a mouthful.
They are.
What are they?
So these are transformations that preserve that special geometric structure,
Right.
the symplectic structure.
Okay.
And they act in a really specific way
Okay.
on certain topological features of our space called homology groups.
Remind me, what are homology groups again?
Okay, so homology groups,
Yeah.
think of them as a way to describe the holes in a shape.
Holes.
Yeah, or cycles.
Okay.
They're like a topological fingerprint
Quite interesting.
that tell us about the structure of a space.
So these symplectomorphisms are like rearranging our space
Yeah.
without changing its fundamental holiness.
Exactly.
A good way to put it.
And the paper's classification,
Okay.
it's presented in Theorem 5.2. It reveals this hidden order
Okay.
within this world of transformations.
It tells us exactly which kinds of symplectomorphisms are possible,
Okay.
based on how they affect those homology groups.
So it's like creating this detailed catalog
Right.
of all the ways to rearrange a puzzle
Exactly.
while keeping the shape the same.
While preserving the overall shape.
It's amazing how this paper finds order
I know. It's pretty cool.
and patterns in these seemingly chaotic transformations
It is.
in higher dimensions.
That's the power of mathematics, right?
I think so.
It gives us the tools
Yeah.
to see patterns
Right.
and connections
That's
that
right.
would otherwise be hidden.
So to bring it all back,
Okay.
we started with this question.
Right.
Can we extend cyclic actions to circle actions? And the answer is more nuanced
It is much more nuanced.
than just yes or no.
Definitely.
It depends on the type of space,
Yes.
the type of action,
Right.
and the interplay
Uh-huh.
between geometry and topology.
Precisely. The paper shows us that even in abstract mathematics, context is everything.
That's a good point.
And it highlights how powerful these tools are.
Like what?
Fixed point analysis,
Okay.
J-holomorphic curves,
Gotcha.
for uncovering these complexities in seemingly simple shapes.
Well, this deep dive has given me a lot to ponder.
It has for me too.
I think I need to go lie down
Uh-huh. I understand.
and contemplate higher dimensional spaces for a bit.
Take your time.
It's been a pleasure exploring this paper with you.
Likewise, the pleasure was all mine.
And to our listeners,
Yes.
I encourage you to delve deeper into these concepts.
Absolutely.
Who knows what mathematical mysteries you might uncover?
You never know, and if you find yourself getting lost
Uh.
in a six-dimensional labyrinth,
Oh, yeah. I can see that happening.
don't worry.
Okay.
Even the experts get disoriented sometimes.
I bet.
The key is to embrace the challenge
Okay.
and enjoy the journey.
I love that.
Until next time, happy exploring.
And that concludes our deep dive
It does.
into the world of periodic, symplectic, and Hamiltonian diffeomorphisms on irrational ruled surfaces.
Quite a mouthful.
We hope you enjoyed exploring this fascinating paper with us,
I did.
and we encourage you to continue exploring
Absolutely.
the amazing world of higher dimensional mathematics.
There's always something new to discover.
Until next time, stay curious. All right, let's dive into some really fascinating math today.
Yeah.
We're talking about symplectic and Hamiltonian diffeomorphisms,
Okay.
specifically on irrational ruled surfaces.
Right.
And this is based on a paper by Nicholas Lindsay and Weiyi Zhang.
Sounds good.
Now, this paper tackles a very specific question.
Okay.
Can every Hamiltonian cyclic action be extended to a Hamiltonian circle action?
That's a great question, and as we'll see, it depends.
It does.
It depends very heavily on what type of transformation you're looking at.
Yeah, and even the type of four-manifold that we're working on.
Right, exactly.
So the paper mentions rational, irrational ruled, and non-uniruled manifolds.
Yeah,
It seems like each one has its own quirks when you're trying to answer this question.
exactly. They all have their own rules.
Yeah.
And you have to be very careful about which rules you're playing with.
Yeah.
And on top of that, we have to distinguish between involutions
Right.
and other cyclic actions.
Yeah.
So an involution is a transformation that's its own inverse. So if you do it twice, you get back to where you started.
All right, so kind of like reflecting something in a mirror.
Exactly like a mirror.
Okay.
And as we'll see, those are sort of the wild cards in this whole discussion.
So before we go any further, can you remind us what exactly we mean by symplectic and Hamiltonian diffeomorphisms?
Sure.
Just a little refresher.
So a symplectic diffeomorphism, you have a smooth manifold, and you want to transform it in a way that preserves a certain structure called a symplectic form.
Okay.
And this form essentially defines how to measure area
Right.
on your manifold.
All right.
So a symplectic diffeomorphism is something that moves the points around smoothly
Okay.
while preserving this area measuring structure.
So it's kind of like if you had a sheet of rubber and you're stretching and bending it, but you're not tearing it.
Exactly.
And you're not changing the total area.
Yeah, that's a great analogy.
Okay, so where do Hamiltonian diffeomorphisms fit into this?
So a Hamiltonian diffeomorphism is a special kind of symplectic diffeomorphism. It's generated by a function called the Hamiltonian,
Right.
and you can kind of think of that as like a potential energy on your manifold.
Okay.
And this potential energy determines how the points flow.
Okay.
And this flow always preserves the symplectic form.
So every Hamiltonian diffeomorphism is a symplectic diffeomorphism,
Right.
but not vice versa.
Yeah, not every symplectic diffeomorphism is Hamiltonian,
Okay.
but every Hamiltonian one is symplectic.
Okay, so they're kind of like a more elite group
Exactly. That's a good way to put it.
within the symplectic ones.
Yeah, and this distinction is important when we try to answer this question of extending
Okay.
cyclic actions to circle actions.
Yeah, and the paper also mentions this idea of a moduli map,
Okay.
which helps us analyze these transformations.
Yeah.
Can you give us a simple explanation of what that is?
So you can think of a moduli map as like a way to project a three-dimensional object onto a two-dimensional surface to kind of see its outline.
Okay.
And so in this case, we have a four-manifold, which is a very complicated thing, and we map it down to a two-dimensional surface called a Riemann surface,
Okay.
which is much easier to understand.
So it's like a trick to make these really complicated transformations a little easier to visualize?
Exactly. It's a way to simplify the problem.
Okay, and then the paper also mentions almost complex structures
Yeah.
and how those are really important for this. Can you explain those a bit?
So an almost complex structure
Yeah.
is a way to equip your manifold with a way of rotating, like
Right.
multiplying by I in the complex plane.
Yeah.
But it may not be a true complex structure. So it may not be what's called integrable.
Got
And that means that certain nice properties that you have for complex manifolds,
Yeah.
you may not have for manifolds with just an almost complex structure.
So they give us a framework for understanding rotations, but with a few caveats.
Exactly.
Got it. And then the paper also goes into this idea of weights associated with cyclic group actions.
Okay.
It sounds like they're assigning numerical values to these actions at specific points.
That's a good way to think about it.
Oh.
So these weights essentially tell you how much the transformation is rotating. at a certain point.
All right.
So, for example, a weight of 2 would mean that it rotates twice as much at that point than a point with weight 1.
So it's a more precise way of describing how these transformations act.
Exactly.
Okay.
And it helps us to distinguish between transformations that might seem similar, but actually have different local behavior.
So we've laid a pretty good foundation here.
Yeah.
Let's jump into the paper and see how they start tackling this question of extending Hamiltonian cyclic actions.
Okay, so the paper starts off by discussing some of the things that are already known.
Okay.
And they point out how the answer to this question depends very much on the type of four-manifold you're looking at.
Yeah.
So if you look at a rational manifold or a non-uniruled manifold, we actually know the answer for all cyclic groups. But if you look at an irrational ruled manifold, that's where things get tricky.
So that's where the real mystery is.
That's where the mystery is. And even within irrational ruled manifolds, there's this big distinction between involutions, which are the Z2 actions, and the other cyclic actions. So ZK actions where K is bigger than 2.
Got it.
So if K is bigger than 2, we know that you can always extend a Hamiltonian cyclic action to a circle action. Although you might have to change the symplectic form a little bit.
Gotcha.
But the question's still open for involutions.
So involutions are the ones that might break the pattern.
Exactly. They're the troublemakers.
Okay.
And so that's what this paper is really focused on.
All right.
I was trying to understand, are there Hamiltonian involutions on irrational ruled manifolds that can't be extended to circle actions?
So the stage is set. We've got our players. Hamiltonian and symplectic diffeomorphisms are setting. Irrational ruled manifolds. And our big mystery. Can all Hamiltonian involutions be extended to circle actions?
Exactly. And we'll see how these authors try to unravel this mystery.
Yeah. Let's see what clues they find.
So the paper goes on to discuss fixed point sets in a lot of detail.
Right, because the points that don't move under the transformation form these special sets that kind of give us information about the transformation itself.
Exactly. They're like fingerprints of the transformation. Now, for ZK actions where T is bigger than 2, the fixed point set has to contain 2 distinct sections. So you can think of a section as a curve on your ruled surface that intersects each sphere in the ruling exactly once.
So they're kind of like a backbone of transformation.
That's a good way to think about it. So for these ZK actions, you need at least 2 of these, sort of guiding the transformation.
So are those sections the fixed points of the transformation?
So the sections themselves might not be fixed point-wise, but they're invariant under the action. So the transformation might move points around on the sections, but it doesn't move the sections themselves.
So it's like sliding points along the section.
Exactly.
But the sections themselves stay put.
Exactly. Now for involutions, things get more interesting. So the authors show that a Hamiltonian involution on an irrational ruled surface can actually have a connected fixed point set. Which means that it's a single curve that intersects each sphere in the ruling twice.
So involutions can kind of break the rules a little bit.
They break the rules. They can have this connected fixed point set. Whereas other cyclic actions need at least 2 pieces. And this difference is really important, and it hints at why involutions might behave differently when it comes to extending them to circle actions. Yeah, I'm really starting to see how this difference between involutions and the other cyclic actions is going to be important here. Yeah, it's really crucial. Now, before we get into the nitty-gritty details of the paper, I want to take a slight detour and talk about Maruyama's classification of automorphism groups of ruled surfaces.
So Maruyama's classification gives us like a roadmap for symmetries of these surfaces.
Exactly. It tells us what kinds of transformations can exist. And how they're all related to each other. One of the key things we learn from Maruyama is that product surfaces like C cross P1 have fewer symmetries than other ruled surfaces.
So they're like the rule followers of the ruled surface family?
Exactly. They have less freedom to move around. And this is important because it sets the stage for understanding why the examples that are constructed in this paper are so exotic, because they defy expectations based on what we might think from a simpler ruled surface.
So we've got this backdrop of Maruyama's classification that tells us these product surfaces are kind of limiting in their symmetries. And then we have this interesting difference in the structure of the fixed point sets
Exactly.
between involutions and other cyclic actions.
Yeah.
I'm really curious to see how this all comes together in the paper's results.
Yeah, so the paper then starts to get into some very intricate territory.
Okay.
It discusses something called Donaldson's question
Okay.
about symplectic Torelli groups and squared Den twists.
Right.
So the symplectic Torelli group is a group of transformations
Okay.
that preserve the symplectic form,
Okay.
but they might change the topology of the manifold.
Okay, so like twisting a donut without tearing it or stretching it.
That's a great analogy. So you're changing the shape,
Yep.
but you're not changing the area.
Got it.
And Donaldson's question
Yeah.
asks whether these squared Den twists are enough to generate all of the transformations that preserve the symplectic structure,
Okay.
but change the topology.
Got it.
And how this relates back to our discussion
Yeah.
is that if Donaldson's question has a positive answer for minimal ruled form manifolds,
Okay.
then that means any transformation that preserves the symplectic form can be generated by Hamiltonian diffeomorphisms.
Okay.
In other words, there's no real difference
Oh.
between these two notions.
So Donaldson's question, even though it might seem unrelated, could have huge implications for how we understand Hamiltonian actions.
Exactly. It ties everything together.
Yeah.
And the paper then constructs an explicit example of a Hamiltonian involution
Okay.
on an irrational ruled surface
Yeah.
that can't be extended to a Hamiltonian circle action.
Wait, so they actually found an example that breaks the pattern.
They found an example that breaks the pattern.
Wow, that's a huge discovery.
And they call this example an exotic involution
Okay.
because it's so different.
All right, this is where it gets really interesting.
Yeah.
Yeah.
Tell me more about this exotic involution.
So to really appreciate how clever this construction is,
Yeah.
we need to dive a little bit deeper into the structure of irrational ruled surfaces.
Okay, let's do it.
So are you ready for some more technical details?
Absolutely. Bring on the math.
Okay, so to understand the construction of this exotic involution, we need to kind of picture an irrational ruled surface.
Okay.
So remember, it's a surface you get by sweeping a sphere along a Riemann surface.
Right. It's like a whole bunch of spheres all lined up.
Exactly. It's a family of spheres.
Yeah.
And the key to this construction is to choose a specific Riemann surface
Okay.
and to define a map from this surface to itself
Okay.
that has a very special property. And this map is called an anti-holomorphic involution.
Anti-holomorphic involution. Okay, that's a mouthful.
It is a mouthful.
Can we break that down a little bit?
Sure. So an involution, as we've said, is a transformation that's its own inverse.
Right.
So if you do it twice, you get back to where you started.
Anti-holomorphic refers to the way this map interacts with the complex structure
Okay.
of the Riemann surface.
Right.
So essentially, it reverses the orientation of complex numbers.
So it's like a reflection, but in the world of complex numbers?
Exactly like a mirror image,
Okay.
but for complex numbers.
Okay.
Now, the specific anti-holomorphic involution that they choose has a fixed point set that consists of a single circle.
So there's one circle on this Riemann surface
Yeah,
where this involution doesn't move any points.
exactly.
Okay.
And here's the really clever part.
Okay.
They use this anti-holomorphic involution to lift the action up to the four-dimensional irrational ruled surface.
Okay.
So essentially, they're using the map on the Riemann surface to define a transformation
Okay.
on each of the spheres in the ruling.
So they're taking this kind of reflection on the Riemann surface
Yes.
and using it to define a reflection on each of the spheres.
Exactly.
Okay.
And because the anti-holomorphic involution had a fixed point set consisting of a single circle, the lifted action on the four manifold
Yeah.
has a fixed point set that's a two-dimensional torus.
Wait, how do we go from a circle to a torus?
So remember that each point on the Riemann surface corresponds to an entire sphere
Right?
in the ruled surface.
Yeah.
So this circle of fixed points on the Riemann surface
Yeah.
actually corresponds to a whole family of fixed points, one on each sphere.
Okay.
And when you sweep this family of fixed points along the circle,
Yeah.
you trace out a torus.
Ah, okay. So you're like spinning this circle of fixed points around to create a donut shape.
Exactly. And the authors prove through some very delicate arguments that this particular involution with its torus fixed point set cannot be extended to a Hamiltonian circle action.
So they found this very specific example
Very specific example.
that breaks the pattern we thought might exist.
That's right.
Wow.
So what makes this exotic involution so resistant to being extended?
Yeah, what's going on there?
So the key is the topology of the fixed point set.
Okay.
So remember for the other cyclic actions where pay is bigger than 2,
Yeah.
the fixed point set has to have at least 2 distinct sections.
Right.
But this exotic involution just has one connected piece.
Yeah.
It's this torus.
Yeah.
And this connectedness
Yeah.
actually creates an obstruction
Okay.
to extending it to a circle action.
So it's like this torus is getting in the way
It gets in the way.
of letting this thing smoothly
Yeah.
become a circle action.
You can't do it.
Yeah.
It's like trying to fit a square peg in a round hole. You just can't do it.
Okay.
And it's really interesting because this challenges our intuition
Yeah.
about how these transformations work.
Yeah, it's amazing how a simple question about extending these actions
Yeah.
can lead to such kind of unexpected and deep results.
That's the beauty of math.
Yeah.
Often the simplest questions
Yeah.
are the ones that lead to the most profound discoveries.
Absolutely. And the paper doesn't stop there. They go on to show that you could actually construct similar exotic involutions in higher dimensions as well.
Exactly. So
Yeah.
this isn't just some fluke
Yeah.
in 4 dimensions.
It's crazy.
This is a general phenomenon.
Mm.
And the way they do this is very clever.
Okay.
They essentially glue together
Okay.
multiple copies of the 4-dimensional exotic involution,
Okay.
along with some other geometric building blocks.
So it's like taking these exotic 4-dimensional donuts
Yeah.
and stacking them together to make even more exotic higher dimensional shapes.
That's a great analogy.
Okay.
And this really reinforces the idea
Yeah.
that exotic involutions are a fundamental part of symplectic geometry.
Absolutely.
They're not just a quirk of 4 dimensions.
So the papers established that not all Hamiltonian involutions can be extended to circle actions,
Right.
and they've even shown that these exotic involutions exist in higher dimensions.
Yeah.
What other kind of avenues do they explore in the paper?
So they explore some very beautiful connections to other areas of mathematics.
Okay.
For example, they discuss how the existence of these exotic involutions
Yeah.
is related to Donaldson's question about squared den twists.
Right. So Donaldson's question is asking if all these symplectic transformations can be built from these squared den twists.
Exactly, if they're the only building blocks you need.
Okay.
And they show that if Donaldson's question has a positive answer for minimal ruled 4 manifolds,
Yeah.
then the exotic involution they constructed
Yeah.
must preserve a complex structure.
So the fate of this exotic involution is tied to this other question
Exactly.
about the nature of symplectic transformations.
Exactly. It shows how interconnected things are
Wow.
in math.
So the paper also goes into a lot of detail about the fixed point sets
Right?
of these exotic involutions.
Yeah.
What did they find there?
So they find that the fixed point set of this exotic involution is what's called homologically equivalent to a fiber of the ruled surface. So in simpler terms, this means that from the perspective of homology, the fixed point set looks like one of the spheres in the ruling.
So even though the fixed point set is a torus,
Right.
it's like topologically,
Yeah.
it's kind of similar
Yeah, it shares some property.
to the spheres that make up the ruled surface.
Exactly. And this observation
Yeah.
leads to some really fascinating connections
Oh.
to other types of transformations on ruled surfaces.
Okay.
So, for example, they discuss something called a fiber den twist,
Okay.
which essentially twists the ruled surface along one of its fibers.
So you're taking one of the spheres and twisting the whole surface.
Yeah, like you're wringing out a towel.
Okay.
And this fiber den twist
Yeah.
also has a fixed point set
Mm-hmm.
that's homologically equivalent to a fiber.
So even though these two transformations are very different,
Very different.
they have this common
Do you
feature
have this common thread?
in their fixed point set.
Exactly.
That's wild.
And it raises some interesting questions about how these transformations might be related.
Yeah, like we're finding a hidden link
Yeah.
between two seemingly distant.
Yeah, exactly.
Right.
It hints at some deeper structure
Yeah.
that we don't fully understand yet.
Absolutely. Now, the paper also delves into the classification
Right.
of finite order symplecomorphisms that act trivially on homology groups.
Yeah.
Can you explain what those are and why they're important?
So these are transformations that preserve the symplectic structure,
Okay.
and they have finite order, which means if you do them enough times,
Yeah.
you get back to the identity. And
Right.
acting trivially on homology groups means that they don't change the fundamental topology of the manifold.
So they're kind of like these stealthy transformations
Here's a gate.
that are preserving the geometry
Yeah.
and the large-scale topology of the manifold.
And understanding these transformations is important because they're kind of like the building blocks for understanding more complicated transformations.
Okay.
So the paper uses this classification
Oh, yeah.
to analyze this exotic involution
Okay.
and show how it fits into this bigger picture.
Okay, so it's like breaking down a complex machine
Yeah,
into its fundamental components.
exactly.
See how it works.
Exactly.
Okay, and what do they learn from this classification?
So they show that the exotic involution belongs to a very specific family of transformations,
Okay.
characterized by certain properties.
Yeah.
They're fixed point sets.
Okay.
And this helps us to understand what's special
Okay.
about this exotic involution
Yeah.
and how it's different from other types of transformations.
So it's like putting this exotic involution on a map
Yeah,
of the symplectic world.
exactly. Giving it coordinates.
Yeah, and showing its relationship to its neighbors.
Yeah, showing how it fits into the big picture.
This has been a truly mind-bending exploration so far.
Yeah, it's been a wild ride.
Yeah, we've uncovered these rule-breaking exotic involutions.
Yeah.
Explored their properties.
Yeah.
Seen how they connect to other areas of math.
Yeah, it's amazing how much
Yeah.
you can learn from a single paper.
Yeah, absolutely. And I know we've only scratched the surface
Yeah.
of this paper. There's still so much more to uncover.
So much more.
So let's take a short break
Okay.
and then come back for the final part of our deep dive,
Okay.
where we'll explore the remaining gems in this mathematical treasure trove.
Sounds good. So, as we go further into this paper, I'm really struck by how important the geometry of the ruled surface is
Yeah.
to understanding this whole question of extensions.
It really seems like the answer to our question
Yeah.
hinges on the specifics of the ruled surface that
Exactly.
we're looking at.
Yeah, and the authors really emphasize this. They
Yeah.
spend a lot of time talking about how
Right.
the choice of Riemann's surface, which is like the base of our ruled surface,
Yeah.
really influences how these transformations behave.
Right. Earlier we talked about Maruyama's classification and how the product surfaces like C cross P1,
Yeah.
they have fewer symmetries
They have fewer options.
than other rule surfaces.
Exactly.
And it seems like that difference
Yeah.
becomes really important when we consider this exotic involution.
Exactly. And in fact, they show that this exotic involution
Yeah.
can't even preserve the product complex structure
Okay.
on a surface like sigma cross S2.
So this exotic involution,
Yeah.
it's like it only exists on these irrational ruled surfaces.
Exactly. It can't live on a simpler surface.
Okay.
It needs that extra complexity.
So it's like the geometry of the base Riemann surface
Yeah.
is telling us what kind of symmetries
Exactly. It's like the base is controlling everything.
and exist on the whole ruled surface.
It's like the puppet master.
Yeah.
And they emphasize this point even further
Yeah.
by looking at the case where the base surface is a torus.
Ah, the torus is always popping up in interesting places.
Right. It's like the donut of mathematics.
Yeah. Yeah.
And when the base surface is a torus,
Yeah.
the story completely changes.
Right.
They show that in this case, every Hamiltonian cyclic action
Okay.
can be extended to a Hamiltonian circle action.
So the answer to our question flips
It flips completely.
when we change the base surface to a porous.
Yeah, it's really amazing.
Why is that? Why does that happen?
So the torus has this very special property.
Okay.
Its fundamental group is what's called abelian,
Okay.
which means that the order in which you do loops on the torus
Okay.
doesn't matter.
Right.
And this has these really deep consequences for the kinds of transformations you can have on a torus.
Okay.
And that trickles up
Yeah.
to the ruled surface that lives on top of it.
So it's like this fundamental group of the base surface
Yeah,
is like a control panel.
exactly. It's controlling everything.
It's controlling the whole ruled surface.
It's amazing how these abstract algebraic properties
Yeah.
have these really concrete geometric consequences.
Absolutely. Now, speaking of connections,
Yeah.
I was really intrigued by how the paper linked the existence of the exotic involution to Donaldson's question
Right.
about squared Dan twists.
Yeah, so Donaldson's question...
Can you remind us about that connection again?
Sure. So Donaldson's question is asking
Yeah.
whether squared Dan twists,
Okay.
which are these specific types of symplectic transformations,
Yeah.
are enough to generate all transformations
Okay.
that preserve the symplectic form but change the topology.
Right. It's like, can you build anything out of Legos
Yeah.
if you only have one kind of brick?
That's a great analogy.
Yeah.
And the authors show
Yeah.
that if Donaldson's question has a positive answer
Okay.
for minimal ruled 4 manifolds,
Mm-hmm.
then this exotic involution that they built
Yeah.
must preserve a complex structure.
Okay.
So it's like the fate of this exotic involution is tied to this bigger question
Right.
about symplectic transformations.
Yeah, absolutely.
And it really highlights how connected everything is in math.
And before we wrap up this deep dive, I wanted to touch on one more thing that I found really interesting.
Okay.
They talked about how even holomorphic involutions.
Right.
So these are transformations that are preserving a specific complex structure.
Right.
They can sometimes have a connected bisection as their fixed point set.
That's a really important point.
Yeah.
Because it shows that this idea of having a connected fixed point set, which is so central to this exotic involution, isn't just a symplectic phenomenon. It can even happen in the holomorphic world.
So it's like this connected fixed point set.
Yeah.
It's like a more fundamental geometric idea.
Exactly. It suggests that there's something deeper going on that controls the structure of fixed point sets.
Yeah, absolutely.
Yeah.
This has been an amazing journey.
It has been a lot of fun.
Yeah, we've explored this world of symplectic and Hamiltonian diffeomorphisms.
Yeah.
Found these exotic involutions.
Yeah.
Seen how they're connected to the geometry of ruled surfaces.
It's amazing how much is packed into a single paper.
Absolutely. And for our listeners, we hope that this deep dive has inspired you to explore the beauty and complexity of mathematics further.
Yeah. Keep asking questions.
Keep diving deep.
And you never know what you'll find.
Until next time.